right, so in this video I wanted to do a sample problem of how we can calculate the moment of inertia in that context, talking about area, where the area is distributed relative to the axis. And so we have this curve right here. It's y equals h over b cubed x to the third. And so that's the top bound of the curve, or the area that we're interested in. We actually are interested in this area here. Don't want to mark it up too much. It's bounded on the right-hand side by x equals b, and we go up to y equals h. So we're not going to put any numbers in for these values. We're going to work with the symbols, and that's okay. So what I want to do is use the very traditional definition of the moments of inertia. Remember that the basic idea is, in this context, how is the area distributed relative to the axis in question? And so these calculations are how we're going to do that. So let's look at the first one, the moment of inertia about the y-axis, which is defined as x squared dA. So the idea here is, if we want to figure out how the area is distributed relative to the y-axis, which of course is here, here's the x, we're going to think of a vertical strip of the, now I don't like my squiggles, a vertical strip of the area in question, and think about where it is relative to the x-axis, or the y-axis. And so that distance is actually measured in x, which, you know, I think maybe could be confusing if you're not thinking hard about it. We might want to put a y here just because it's IY, but thinking again that what we're talking about is how that area is found, like what distance it is from the y-axis, and then you can understand that the x value does make sense. Now this area here, dA, again, thinking of the area as a long skinny rectangle, has a height. It's bounded on the top by the curve, so the top value of it is the y value, y. It actually goes down to the x-axis, so the y value at the bottom is 0, and then the width of it is dx. So the dx tells us, as well as the x squared, tells us that we're actually going to integrate over x. So we need to express this y in terms of x, but we have the equation of that top curve, and so that's relatively simple. So we'll have h over b cubed x cubed dx. And so this is what the area dA looks like. So I can substitute that into this expression here. And since I'm going to integrate over x, I'm going to go from 0 to b. Now, to just kind of clean up that integral before we integrate, I'm going to put the constants out front. And when we do the integration, so we end up with the integral of x to the 5th, because we have the x squared times the x cubed. So the integral of x to the 5th dx. When we integrate it, we get x to the 6 over 6. And then we have to evaluate it at b and 0. The fact that we have a 0 lower limit is nice because it's less evaluation for us. And so we get h over b cubed times b to the 6th over 6, which ends up to be h over 6 b cubed. And so that becomes the moment of inertia about the y-axis. Let's do a similar calculation, but let's calculate the moment of inertia about the x-axis. And so I'm going to have to erase a little bit of the stuff that I drew on this picture if I want to use it again. Because if I'm thinking about how the area is distributed relative to the x-axis, I'm thinking about the area in a strip. This is the dA, and it's measured some distance y from the x-axis. So my dA has to be written differently this time. Now it's bounded on the right by this value of x, which is x equals b, and bounded on the left by the x value here, which I can find by rearranging the expression for that curve. Right now it's written as y equals. I want to write it in terms of x equals. So just to break it down in a little bit more detail to think about it, so what I was really saying is that the dA represents the width times the height, where the width is found by taking the x value on the right-hand side minus the x value on the left-hand side. And then the height is actually equal to dA. So on the right-hand side, the x value is just b. And on the left-hand side, I have to really rearrange all of this and solve for x. So I'm going to get b cubed over h times y, and all of that raised to the 1/3. That's the x. That's not that pretty. And then times dy. So this is what I'm going to have to put into my integration for dA. You can see that this one is not as friendly. Oh, and the limits are going to be, we're integrating over y this time, so we go from 0 to h. So I have y squared times b minus b cubed over h, the cube root, and y to the 1/3 dy. So when I do that, my integral is going to be b y squared minus the cube root of b cubed over h. Now when I take y squared times y to the 1/3, I'm going to get the y squared I can write as 6/3 times y to the 1/3 will give me y to the 7/3. Okay, so you can see this is getting a little light, so I'm probably going to have to switch pens. So I'll do that down below so we can see what our integral is. So I'm just going to rewrite the integral because it was a little hard to see here. My integral that I'm doing is 0 to h by squared minus b cubed over h, the cube root of that, times y to the 7/3 dy. So let's, oh, and this is going from 0 to h. I don't know why I wrote a b. I think I said h, but I wrote b. All right, so let's integrate this. I get by cubed over 3 minus the cube root of b cubed over h, y to the 10/3 times 3/10. That's when I divide by the 10/3, I get that 3/10. And I'm going to evaluate this at 0 and h. So this is going to be b h cubed over 3 minus the cube root, and I'm going to do something here, the cube root of b cubed over h. But I can also put the y to the 10/3 inside the cube root and just keep it y raised to the 10, but the cube root is taken care of outside. So I'm just going to say, and y raised to the 10, when I evaluate it at h, it's h raised to the 10, and then times the 3/10. 3/10 is just going to stay out there because that's where it belongs. So we can actually simplify this a lot because actually notice this. If I get rid of one of the h's, then this is h to the 9. And now I'm going to take the cube root of that thing. So I have bh cubed over 3 minus 3/10. I'm just putting the 3/10 in the front. The cube root, it's going to be the cube root of b cubed h to the 9th, which is going to give me bh cubed. Now, if you see that, you notice that we have that common bh cubed, but we're really doing 1/3 minus 3/10. And now I just can find a common denominator of the 3 and the 10. That's going to be 30. So 1/3 is going to be 10. And 3, that's going to be 9 bh cubed. And I'm going to get 1 over 30 bh cubed. And so that is the moment of inertia about the x-axis. Now, in the next video, I'm going to do this calculation of Ix in a different way because this was kind of unpleasant. I mean, it's not like super hard dealing with it, but let's look at doing it a different way.